Okay, hey guys. So I think that point sources and collimation are probably among the most abused terms in optics and optical design, but not by optical engineers. In my personal experience, I've encountered a lot of situations where you've got a technical team in R&D, engineers, managers, directors, whoever, who tend to use these terms like they are the one fix all solution for almost everything. It's like, oh, you got an illumination problem? Oh, use a point source. Or, oh, you've got an illumination problem? Oh, use collimated beam, right? And then it's interesting because that can happen even when you've got an optical engineer in the room and a manager or a non-optical engineer or someone else proposes those as solutions and not even ask the optical engineer, oh, by the way, am I right? Does this make sense? Am I making sense? It takes a lot of humility, understanding, and mindfulness to realize that we have limitations. I, as an optical designer, am limited in so many ways, even in optics. In everything else, I'm an idiot. I don't know anything. And that's going to be the first thing I would tell you in basically any situation. So anyway, in this video, I'm going to try to clarify what collimation really means and that it doesn't always involve parallel rays. In fact, most of the time it's divergent rays. Okay, and I'm going to limit the case to incoherent collimation. If you're collimating a laser Gaussian beam, for example, that's a whole totally different story, right? You probably would know that if you're a laser physicist. So anyway, I will also have to make reference to point sources, unfortunately, because I've got to put a point source at the back focal plane of the lens to collimate it. But point sources, just so you know, they don't really exist. If you even if you let's say if you go back to read the papers of classical radiometry by Nicodemus is you'll never see you'll almost never see an optical radiometry paper without referencing to Nicodemus. And in one of his famous papers called Radiance, I think it was called, and I think it was published in the American Journal of Physics, he makes a statement saying, therefore, there can be no such thing as point sources, idealized point sources, right? But it's not just because he said it. Think of it this way: a point source is an idealized mathematical construct. It doesn't really exist in real life, but mathematically, in a calculus way, in a limiting case, they can exist. For example, okay, direct delta function, right? They don't exist in real life, but if you take a Gaussian function and take the limiting case in which the width goes to zero and the peak goes to infinity, you get something very close to a direct delta function. What's a point spread function? A point spread function is a distribution of light at the back focal plane of a lens when you've got a point source or a source at infinity. But you can't put a source at infinity because you can't go to the edge of the universe, right? What you have instead in the lab, if you see a point spread function, is something very close to it, but not exactly it, because the source will always have a finite size. Waves, light waves entering an aperture will not be exactly plane waves, and the lens has its own errors as well. So what you'll see is a distribution of light at the back focal plane that is very close to being a point spread function, but it's not exactly a point spread function. Okay, so that out of the way, now I'm going to talk about collimation. Right, so on my screen here is the interface for ZMAX Optic Studio, and I've got a layout of three fictitious thin lenses. Okay, they're fictitious, but they're idealized fictitious lenses, thin lenses. And the wavelength is not really relevant because these fictitious lenses are non-dispersive. But anyway, just so you know, I've got it at 550 nanometers, and I've got an axial point source whose rays are being collimated by the first lens, which I have called a flux collector. Later on, you'll see what I mean, why I call it a flux collector. So the flux collector, this lens here, has a effective focal length of 25 millimeters. So when I put a point source at the back focal plane of the first lens, the flux collector, the rays come out collimated. They're parallel, right? Okay, great. But in reality, if you have an LED, for example, with a 2 millimeter diameter, then that's an extended source, right? So if I show what happens if I have the second field point right here, if I just kind of zoom in, I've got two point sources, idealized mathematical constructs. A point source at the axial position, and another point source at the off-axis position. And the beams come through the lens, and they come out collimated. Now, it's still collimated. These rays are still collimated, but guess what? I've got a divergent beam now. I've got the axial beam going straight here, and I've got the off-axis beam diverging at an angle down this way. In fact, to make it more realistic, or look realistic, let me add a third field point, and now you see a really divergent beam. If I have many, 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 many rays here, let's color rays by wavelengths. Let's see. Okay, so it's all green, and let's put 111 rays. I always use odd numbers of rays so that I can have a central ray. If I put even numbers, I don't see the central ray. Okay, so here's a divergent beam. So here in reality is a divergent beam, but they're actually still collimated. They're still collimated. So the test for collimation is when you put a second lens, what happens to the beam at the back focal plane of the second lens. So the second lens is called a collimator here. I call it a collimator. And the back focal plane is right over here. And you can see a focus, right? Three focal positions, or three focal points, because I've got three light sources. 1, 2, 3. The back focal plane here is 200 millimeters because the focal length of the second lens is 200 millimeters. So that's the test for collimation. The test for collimation is if you put a second lens to the right of the first lens that's said to be collimating a beam, then at the back focal plane of the second lens, you should see a focus of the rays from the source. Okay, so now let me go back to making things look a little simpler by giving it, again, 3 rays per field. And okay, so like this. Now I've got a third lens. I call it an objective lens here. Why? Because this whole system of lenses here represents a thin lens paraxial layout of a typical fluorescence microscope in the excitation path. Okay, fluorescence is what happens. Fluorescence is if you shine light onto an object and the object is fluorescent, then it absorbs the light and emits light at a longer wavelength. That's fluorescence. The light that is being emitted is fluorescent light, or just the emitted fluorescence. So in a fluorescence microscope, you usually have an exciter, and then which is the system that you see here, and then you collect the emitted light in the what's called the return path, right? So you would normally have a flux collector, a first lens, and then a collimator, which is a second lens. Sometimes you call it a field lens, but you can call it a collimator or a field lens, doesn't matter. I call it a collimator because, again, I'll show you in a minute why um, why collimation is actually a relative term. And then the third lens is your objective lens, again represented by a fictitious thin lens with in this case, a 20 millimeter focal length. And at the right side of the objective lens, I've placed, a sample, maybe a fluorescent sample. In a typical fluorescence microscope, what happens is you would actually have a mirror here. You normally you would have a beam splitter, right? It that would reflect the beams down to the objective lens and then onto the specimen. The specimen, if it's fluorescent, will emit fluorescence, and it will go back through the objective lens, but through the beam splitter and up to a microscope, so-called tube lens, which focuses the rays onto a camera. Right. So what I'm showing you here is just the excitation path, the illumination path. So here is another concept of collimation in that it is a relative term. You're collimating rays. When you're collimating rays relative to a plane, right? So the first lens is collimating rays relative to the LED. Here, let's call it an LED. Okay, it's an LED. But in this first space here, is collimated rays. It's collimated space. Even though you see a divergent beam, again, it's collimated space. Okay. In the second space here, it is convergent space for rays coming from the source, but it is collimated space for rays coming from this aperture, which is in the terminology of fluorescence imaging, we can call it a field stop. You can call it a field diagram or a field stop, but it really is a physical aperture placed, located at the back focal plane, or okay, if you consider the left side the front and the right side the back, it's located at the front focal plane of this collimating lens. Therefore, the rays are collimated. So to see that, let's color the rays again. Let's color it by field, and let's put just two fields so that it's not so complicated. All right. So remember, I said that the test for collimation is that if you put a second lens to the right of the first lens, that at the back focal plane of the second lens, you should see a focus of rays coming from the source. Let's consider the aperture the source relative to the second lens. If that's the source, then two rays that intersect at the source appear like they're emitting from the source, right? So they're emitting these two rays here, okay? The axial on-axis ray, the central ray, and the off-axis central ray, which is called the chief ray and the axial ray, they come diverging from this point, and then they pass through the second lens. Of course, since the axial ray is going through the center of the lens, it is just passing through. But look at what happens to the chief ray. It hits the lens and becomes parallel, refracts and becomes parallel to the axial ray. So they're collimated, right? They're collimated by the second lens from this intermediate source, which is the aperture. And what happens to the rays? These two rays, if you follow it closely, continue on. This axial ray continues on all the way to the sample plane here. This chief ray continues on until it hits here, bends down to a focus. So in optical terms, this sample plane here is called a conjugate plane to the aperture, the field stop. So in a fluorescence microscope, there are two conjugate planes. The first conjugate plane is the source and, in this case, the back focal plane of the objective lens. Right here, if you put a business card, you'll see a projection of the source. If it's an LED, you see the LED right there. The second conjugate plane, pair of planes, would be from the aperture, the field stop, and the sample plane. These are conjugate planes. And by the way, this is called a color illumination setup. In this setup, we purposely project the source into the back here. If the source has some structure to it, some hot spots and cold spots, then all of that is projected to the back here. But guess what? When they come out through the objective lens, they homogenize at the specimen plane, the sample plane. You see, this axial ray hits here, the off-axis ray gets bent, it's here, and many of such rays just come together and superpose at the sample plane, and that is the homogenization effect of color illumination. So now you see that getting a good understanding of what collimation really means allows you to set up a complicated optical system like this and know where to put your lenses to be able to get a practical good result, but in this case, a uniform illumination onto the sample plane in fluorescence microscopy. Okay, so I hope that this is clear for you, and I wish you good luck and all the best. Thanks. Bye bye.